Hi everyone and welcome back to my channel. I'm Anish and today we'll start with the assignment solutions that I gave you as homework in the previous lecture from cache memory. So let's start with the first question. So a computer has 256 kilobyte four-way set associative write back data cache. Okay, a lot of information is given. Block size is 32 bits. Okay, so first of all let's reduce the information. So it is 256 kilobyte cache. So it has 256 kilobytes of cache size. So cache size is 256 KB. Block size is equals to 32 bytes. Okay, so byte offset will be what? Byte offset. This will anyways be required, so it does not matter because anyways they are asking number of tag bits. So anyways byte offset will be required. You anyways calculate it. So this will be log of base to 32. This will be equals to 5. Now now they are telling me that the processor sends 32-bit address to the cache controller. Basically, that means the main memory address has 32 bits. So main memory address has 32 bits. Okay, main memory address has 32 bits. So then each cache directory each cache tag directory entry contains any in addition to address tag the two valid bits, one modified bit and one replacement bit. So basically extra tag bits, right? Because addition to the address of the tag bit, that is the unique identifier, I have these extra tag bits. So I will write here extra tag bits. Extra tag bits. Okay, so extra tag bits will be two valid bits, one modified, one replacement. So it will be 2 plus 1 plus 1. Okay, I don't like, you don't have to worry about the functionality of what is valid bit, what is modified bit. No, just whatever they have told you, you just write that down. That's it. Okay, just focus on the numericals. So 2 plus 1 plus 1, that is 4. So 4 bits, 4 extra bits I will have to add after finding out the tag size. Okay, so they are asking the number of bits in the tag field of an address will be, how many bits will be the tag. Okay, so of course this 4 bits will be there and I have to identify the tag size as well, tag bits. Okay, unique identifier. So if I know the cache size, if I know the block size, number of blocks, it will be 256 kilobytes. Divided by 32 bytes. Okay, so it will be equals to 256 divided by 32 bytes. So 256 divided by 32, so it is 8 kilo, right? 8 kilo means 2 cube into 10, 2 raised to power 10, that is 2 raised to power 13. Number of blocks is 2 raised to power 13. How many bits required? Number of bits. Now I have to find out the number of sets. How many sets will I have? It is a four-way set, right? Four-way set. It is a four-way set. So number of set will be what? Number of sets. So number of sets will be basically total number of blocks, that is 2 raised to power 13 divided by the set number, that is 4, associativity. So it will be 2 raised to power 11. So how many bits do I require to basically define the sets, right? Bits, set bits, number of bits for set field, it will be 11, right? Log of 2 of 2 raised to power 11, that is, it will be 11. Okay, 11 bits will be required. Okay, so 11 bits are required. So how many will be the tag bits out of this? So tag bits will be equals to total main memory size. What is the total main memory size? 32 minus set number of bits required for set plus the byte offset. Number of bits for byte offset is 5. So it will be 5, 16. So it will be 16 bits. It will be 16 bits. Okay, so it is 16 bits. Now if it is 16 bits, what can I comment? I can comment that so tag size, tag bit is 16 and 16 is present in the option and you will tick it. Okay, okay, number of bits in the tag field will be 16. Yeah, that is correct. Tag size is 16, so number of bits in the tag field of an address will be 16 only. But what is the tag directory size? Tag directory size will be different. Okay, tag directory size will be different. What will be the tag directory size? Tag directory size will be basically this whole, this bits already I have, tag bits plus the extra bits, that is 4 bits. So total tag bits, because ultimately I have to store it in the directory, right? So it will be 20. Now tag directory size, what will be the tag directory size? So the tag directory size will be this 20 into the 2 raised to power whatever the value is. So 20 bits into 2 raised to power, how many number of cache blocks I have? Number of cache blocks is 2 raised to power 13. So it will be 2 raised to power 13. So if I want to convert this into kilobytes, it will be 20 kilobytes. Okay, this will be the cache directory size. So somewhere it is not present, so I am doing some mistake. What kind of mistake am I doing? So okay, sorry, they have asked, remember, okay, they have asked in bits, they have asked in bits, they have not asked in bytes. So this is in bytes, I am talking this is in bytes because simply what I have done is I have divided by 8 as well and I have divided by 2 raised to power 10. But as they are asking in bits, so this will be 20 in 20 kilo into 2 cube bits because they are asking in bits. So this will be 8 into 20, so 160 kilobits. So you should know the conversion between bits and byte. Okay, so 160 kilobits. So option A will be the correct answer for this question. So 54 and 55 we have done. This was in set, this was in GATE CS 2012. So now let's solve the next question. Here we have the width of the physical address on a machine is 40 bits. So main memory width is 40 bits. So main memory width is 40 bits. The width of tag field in a 512 kilobyte 8-way set cache will be what? So there is a shortcut actually. There is a shortcut. What is a shortcut? I will tell you the shortcut. So if my, like of course you can solve with the basics we already know, so I will not explain the basic method, that will be same only. If let's say I know the byte offset is x, here right, they have not given me what is the byte offset, they have not given me what is the byte offset, right? They have not given me what is the byte offset. So how do I find out what will be the tag size? So it is a 512 kilobyte 8-way set associative, correct? 512 8-byte set associative. So the combined effect of the byte offset and the set number, can you tell me what will be the combined number of bits for the byte number and set associative? That will be the cache memory size. If you remember, what is a set offset formula? Set offset formula is equals to number of blocks divided by the block size, correct? So now set offset is number of blocks divided by cache size, and I know what is the cache memory size. So cache memory size equals to block size into number of blocks. correct? So individually, so here I can replace this with the, like this, what will be the block size? Block size will be number of blocks divided by the set of set. uh, I'm just figuring something out, number of blocks. Okay, so block size is equals to, yeah, so basically if I am able to find out, let's assume the byte offset is x. Okay, let's assume the byte offset is x. If the byte offset is x, that means what is the block size? Block size will be 2 raised to power x. Block size will be 2 raised to power x. And so what is the number of blocks? So if I go number of blocks will be equals to what? The cache memory size, divided by the block size, that is 2 raised to power x. So cache memory size is what? Cache memory size is 500, I guess it is 512 kilobytes. So it is 512 kilobytes. So that this will be equals to 500 into 2 raised to power 13 bits, correct? And divided by 2 raised to power x. So 512, okay, this will be my number of blocks. So this is my number of blocks, right? But I don't need number of blocks. I actually need number of blocks. Okay, sorry, here, right, set offset is not equals to number of blocks divided by the block size. I'm wrong. It is equals to the set number, right? Set associativity. That is what I was going wrong. Set number. Okay, so the set offset will be, my set offset becomes 512 into 2 raised to power 13 divided by 2 raised to power x. Now assumption is block size is also in bytes. If it is in bytes, right, here I don't need to convert this into bits. So this, right, should be in bytes, because assumption is my block size is also in bytes only. So this is bytes and this is also bytes. Okay, so now, like, what we can do is we can this will be 0, and set offset will be like it is of, I guess, 8 way set, right? 8 way set is 2 raised to power 3. So it will be 8 divided, this is what? This is 2 raised to power 9. So this will be overall 2 raised to power 16 minus x. So the number of bits in the set offset, number of bits in set offset, this will be equals to 2 raised to power 16, sorry, 16 minus x, right? Basically I am doing log of 2 raised to power 16 minus x. So it will be 16 minus x. So ultimately, right, if your block is x, then this will be 16 minus x. So ultimately this whole thing, right, is always equals to the log of the cache memory size. Cache memory size. If you notice, if you observe this thing, it will be always the log of the cache memory size, where currently it is what? Log of cache memory size is 512 kilobytes. So it is, okay, it is not equal, actually no, cache memory size divided by the set associativity. Cache memory size divided by the sets. So it is 4 sets. So this will come out to be 2 raised to power 16, because block size anyways gets cancelled. Block size anyways will get, yeah, block size anyways will get cancelled if I multiply these two things. So ultimately this comes out to be 16 only. So that's why you don't need to actually calculate this individually. If you don't want, you don't need the block size. You assume these to be a whole 16-bit field, and the remaining one will be the tag field. They are just asking the tag field. So overall this is 40-bit field, and 16 bits are gone for these two fields, set and the byte offset, set and the byte offset. So the other field will be the tag. Other field will be the tag. So now I can directly say the number of tag bits number of tag bits will be equals to what? Number of tag bits will be 40 minus 16, it will be 24 bits. 24 bits. Okay, so 24 bits will be the answer of this question. Very beautiful question. You don't need to actually calculate the whole block. It does not matter. It does not matter even if it is xy, right? Even if it's xy, if it's 8, 16 way, uh, 1 way, 2 way, does not matter. Okay, the number of tag bits will not change. Number of tag bits will not change. Okay, so number of tag bits will not change. So I hope you have understood this basic points. So it will be 16 only, it will be 24 only, sorry, it will be 24 bits only. It does not matter what way it is. Let's now solve this question. If cache contains 2 raised to power 16 blocks and the main memory contains 2 raised to power 24 blocks, what is the size of the tag directory for a fully associative cache? Okay, what is the size of the tag directory for a fully associative cache? So what I have to understand, let's take few examples. Let's take very small examples. So let's assume that my main memory has 4 blocks. Okay, main memory has 4 blocks. This is block 1, this is block 2, this is block 3. Okay, so this is block 1, this is block 2, I'm sorry for the noises outside, and this is block 3. Now I don't care what is the byte offset. Like each blocks can contain 4 bytes, can contain 8 bytes, I don't care. Okay, let's assume each blocks contains x bytes. So each block contains x bytes, okay. So if each block contains x bytes, I don't care. Okay, now again the same in the cache memory. If I am in the cache memory, let's say I have only 2, it is a fully associative. So if it's a fully associative one, that means how many blocks will I have? 4 blocks, right? I will have 4 blocks here. How many tags will I have? 4 tags, correct? I will have 4 tags. 1, 2, 3 and 4. So this will be 1, 2, 3 and 4. So this will be here. So this is fully associated, right? So I will have 4 tags here, 4 tags, correct? So what will be the number of tag bits? Number of tag bits will be basically, okay, sorry, no, I will not have 4 tags here. Whatever is the number of blocks I have. Let's assume that my cache has only 2 blocks, right? My cache has only 2 blocks. Overall my cache contains only 2 blocks. So if it contains 2 blocks, that means I will have only 2 blocks. It is fully associative. So it will start from 0 here and 1. And what will the tag contain? What will this tag contain? This tag will actually contain the whole block address, right? This tag will contain the whole block address. Why? I will explain. So let's assume this is block. Okay, let's start with 0, 1, 2, 3. Let's not start with 1, 2, 3, 4. So this will be 0, 1, 2, 3. This will be 0, 0, 0, 1, 1, 0, 1, 1. So how do I identify the tags? So currently there will be 2 tags, right? Currently there will be 2 tags. That is fine. So which things will be present in the block 0 of cache memory? 0, 0 and 1, 0, correct? 0, 0 and 1, 0, that is 0 and 2, correct? Block 2 and block 0, and in 1 there will be block 1 and block 3. So what is the tag? What is a tag? How do I identify? Tag is the whole block, right? Whatever is the address of the block, that is the whole tag, correct? This whole 2 bits. whole 2 bits is the tag. Okay, I cannot choose only a single bit, I cannot choose the last bit, right? Why? The whole block will be the tag, because then only I will be able to identify which block it is. Is it the block 0 or is it the block 2? So how do I identify this? The whole bits of the block needs to be stored. Okay, whole bits of the block needs to be stored. Got it? So how do I find out this 2 bits? Okay, if it was, let's say, 8, then how many bits it would have been? 3 bits, because each block needs to have a unique identifier. That particular block will be placed in block 0 and other blocks will be placed in block 1. Okay, so each block will have a unique identifier known as block number. So the tag bits, right, in a fully associative memory, the tag bits will be the whole block number. So conclusion is in tag bits, if it's a fully associative, sorry, if it's a in fully associative, fully set associative, in fully set associative, I know the what will be the tag bits basically. So basically the tag bits will be the log of number of blocks in main memory. So here, right, I had 4 blocks, so log of 4 is 2, that's why I require 2 bits for the tag field. If I had 8 blocks, log of 8 will be 3, so I will require 3 bits for the tag field. So let's go back to the question. In the question they have told me cache has 2 raised to power 16 blocks, but my main memory contains 2 raised to power 24 blocks. So to uniquely identify all of these 2 raised to power 24 blocks, how many bits will I require? So it will be log, so it will be log of 2 raised to power 24 bits. Okay, so this will be equals to 24 bits. This will be 24 bits. Okay, this will be 24 bits. 24 bits will be required as the tag bits. Now what is the size of the tag directive? Size of the tag directive will not change. Size of tag directive formula, size of tag directive formula is the tag bits, size of tag bits into the size of tag bits into the number of cache memory blocks. So this will be equal to, like, tag bits will be 24 into 2 raised to power 16. So overall this will be 12 into or 8 into 3. Okay, so whatever is, this is bits, right? You can convert this into your result, you can convert this. So this will be the answer of this question. So that this is a very, very good question actually, because fully associative mapping you might have some doubt. So this is another important key point that you must keep in mind. Okay, so cache memory blocks is 8. Look, so let's go to the next question. So we have like a lot of questions in the pipeline, so we have to solve all the questions. So here I have a question where the cache memory has 8 blocks, main memory has 32 blocks, and block size is of 4 bytes. Okay, cache memory has 8 blocks, main memory has 32 blocks, block size is 4 bytes. So the number of bits for the block, number of bits for block will be 2. Okay, basically it is log of 2 base 4 equals to 2, and main memory will be of 32 blocks. So if main memory is of 32 blocks, it will be log base 2 of 32 So not 32, sorry, main memory has 32 blocks, okay. Cache memory has 8 blocks, okay. Cache memory has 8 blocks. And what are they asking? For the main memory address, this find the tag, cache block number and offset, okay. And they have not told me about anything about the associativity, so my assumption is it is direct associativity, okay. That is my assumption, that it is direct associativity. So as it is direct associativity, so sorry, it is not associativity, it is direct mapped cache, direct mapped cache. So here I can directly say that main memory blocks is this. For main memory of this address, then find the tag, cache number and the offset, okay. So okay, so let me divide first, let me divide my main memory address. Main memory address is of 8, it seems like main memory contains 32 blocks and each block is of 4 bytes. So what is the total main memory size? 32 blocks, so this will be log of 32, so this will be 5 bits, 5 bits plus 2. So overall main memory, this is my main memory, main memory will contain 7 bits. Main memory will contain 7 bits. Main memory will contain 7 bits, okay. So main memory will contain 7 bits. Now now from here, right, how many bits will, what will be the byte offset? Byte offset will be 2, right? This will be the byte offset, 2 bits. Okay, then this is my number of cache memory blocks, number of cache memory blocks, no sorry, not number of cache memory blocks, this is direct map. So direct map, this will be the, yeah, number of cache memory blocks. Basically what is the number of 8 blocks I have cache memory, so here I will have 3 bits, so this will be 3 bits because log of 8 is 3. And this will be the tag bits, so tag bits will be what? Tag bits will be 5 minus 7, that is 2. So 2 bits will be tag bits. Two bits will be tag bits, okay. So this will be the number of tag bits, this will be the number of basically my cache blocks, and this is that. So they are asking what is the tag, so out of this which one will be the tag? So tag will be the first 2 bits, tag will be the only the first 2 bits, okay. So let's break it down. So 0x1, so let's solve the first question, 0x1a. So if I break it down into binary, so this will be 1 0 0. So main memory is only of 7 bits, right? So I will convert this into 7 bit. So this is currently 8 bit data, 0 0 0 1 0 0 0 1 1 0 1 0, okay. So this will be 16, sorry, this will be 2. So this is my main memory address. Basically out of this the first 2 bits will be the tag, so tag is actually 0, so my tag is 0 0 in binary, that is 0, okay. What about the cache block number? So cache block number will be equals to, they have asked the cache block number, cache block number will be equals to the next 3 bits, so it is 110. So here the next 3 bit is cache block number, so it is 110 of 2, so this will be 2 plus 4, that is 6, okay. So next is the last 2 bits, that is the byte offset, this is the byte offset, right? So my byte offset byte offset is equals to 10, that is 2. Byte offset is basically 2. Okay, so yeah, it is 10, so it is basically equals to 2 only. Okay, so the different components I hope you have understood. Okay, now let's solve the next part of this question. Okay, sorry, next part of this question. So the next part of this question is here: determine if it results in a hit or miss if the cache currently stores the following data. So if the main memory call is this 0x1a and the cache block has this, like cache has 8 blocks, so that's why 8 blocks currently has this data, and this is the tag and this is the valid bit, whether it is valid or invalid. So everything is valid here. So they're asking me whether it will be a hit or miss. So I have found out what is my cache memory block number 6. So I will go into the cache memory block number, that is 6, and I will check the tag. Tag is 2. What is my tag here? Tag is 0. So is the tag matching? Tag is not matching. So here this is 10. Yes, it is correct. 110. This is 00. This should be 110. Yeah, it is correct only. Yeah, it is not. Yeah, it is correct. 7 bits will be the address. That is what I'm observing. I'm just trying to see if something is wrong or not. Okay, so yeah, currently my tag is 0, but here tag is 2. So tag is not matching. Tag is not matching. So if tag is not matching, that means what? If tag is not matching, that means basically what we have to do? We simply have to, it is a cache miss, right? We simply have to again bring the data back to the cache memory. So as tag is not matching in the given cache block number, we have to, it will be a cache miss. It will be a cache miss. Okay, as the tag does not match, it will be a cache miss. Okay, so yeah, that is the case here. Now let's solve this question, question 23. So consider a 64 byte direct mapped cache with a block size of 16 bytes. The main memory size is 256 bytes. Currently the cache block have the same following tags. So consider a 64 byte, it is a direct map cache and block size is 16. So what will be the byte offset? Byte offset will be log of 216, so it will be 4. Okay, and it is a 64 byte direct mapped cache. So cache memory size is 64 bytes. Okay, the main memory size is 256 bytes. Okay, main memory size is 256 bytes. Currently the cache blocks have the following tags. It has the following tags. This is the block. I have 4 blocks, and out of the 4 blocks, these are the tags. Okay, so what are they asking? They are asking main memory byte number 61 and 141 are present in the cache. How do I check it? So I have to basically take the mod, right? How many blocks I have in the cache memory? 4 blocks, because each block contains 16 bytes and overall cache memory has 64 bytes, so it will contain 4 bytes only, right? 64 divided by 16, it will be 4 bytes only. So I have to check which one is correct and which one is false. So if I check here, currently, like, number of cache blocks, number of cache memory blocks will be 64 byte divided by 16. 16, yeah, 16, like, because block size, right? Block size, so it will be 4. So I have 4 like number of blocks in the cache memory. So where will the byte number 61 will be stored. So byte number 61 is present in the which block, that I have to understand. Byte number 61 is actually present in the which block. So I have to again divide this main memory into different components. So it is direct map. So my number of bits for cache block will be what? Log base 2 of 4. Log base 2 of 4. So it will be 2. Okay. Then the number then what we will do is, then we will find out the uh, number of cache memory. So then I will find out the byte offset. So what is the number of byte offset? I have already written, right? Yeah, byte offset is 4. So 4 bits is for byte offset, 2 bits is for the cache memory block number. So overall, what is the main memory size? 256 bytes. So if it is 256 bytes, so number of bits in the main memory, in main memory, it will be log base 2 into 256. So it will be 2 raised to power 8. So it will be 8 bits. It will be 8 bits. Okay. So this will be equals to 8 minus like number of tag bits. I'm just finding out number of tag bits. Tag bits will be 8 minus 2 plus 4. 8 minus 2 plus 4. So this will be 2. 2 will be the answer here. Okay. 2 will be the answer, number of tag bits. Now let us divide our block. So if I write down my like main memory address, in the main memory address, the I think for byte offset we have 5 bits, I guess. No, 4 bits. For byte offset I have 4 bits. For cache memory block number I have 2 bits and 2 bits for the tag. So here I have tag, here I have cache memory block, and here I have byte offset. So byte offset will be here 4 bits, cache memory block number will be 2 bits, and tag will be 2 bits. Okay. So let's see whether 61 is existing or not. So if I see 61, what is 61? 61, it is in decimal, right? 61 is in decimal. Okay, if nothing is mentioned, by default you will assume 61 to be decimal. So how do I write 61? 61 is 32 plus 20 32 plus 29, I guess. Yes, 32 plus 29. So what is 29 equals to? 29 is equals to 16 plus 13. What is 13 equals to? 13 is equals to 8 plus 8 plus 5. What is 5 equals to? 5 equals to 4 plus 1. Okay, so I guess I have done everything correct, right? 32 plus 16 is 48. 48 plus 8 is 56. 56 plus 4 is 60. 61. Yes, it is correct. So basically in binary, what it will be? This will be bit position 1. This will be the bit position 2 here. Then I will have bit position 3 here. Then I have bit position 4 and 5. Yeah. So it is 0, 1, 2, 3, 4, 5. Yeah, everything is correct. So this is my binary equivalent. But remember, my address is 8 bits long. So what is it currently? Currently it is 4 plus 2, that is 6. So it is 4 plus 2, that is 6. I will need to append more 2 bits. I will need to append more 2 bits. So overall it will be 4, 4, 8 bits. Okay. So now I will divide this back. Now I will divide. So from here I can divide. The first 2 bits will be the tag. So this is tag is 0. And the next 2 bits are my cache block number. Cache block number here is 3. And the last 4 bits are the byte offset. Byte offset from here I can see is 1 plus 4, 5 and plus 8, that is 13. Okay. So I don't care about the byte offset. I just care about the tag and the block number. So if I see block number 3, if I go here 10, it is tag 0. Yes, it is matching. Block number 3 and tag 0 actually is matching. Okay, so 61 is present in the cache, that is correct. 61 is present in the cache, that is correct. Okay. Oh no, sorry, this is block number 11. This is not 3, right? 11 is here. Sorry, 61 is not present. So this is 11, right? That is 3. So block number 3 and tag is 1. Here tag is 0. So it is not matching. So not matching. So for the first option, it is not matching. Okay. So tag not matching, right? So let's check for the other one. Other one is 141. Okay. 141. For 141, again I will do that process. So it will be 128 plus how much is it? 3 plus 13, right? 13. So 13 will be 8 plus 4 plus 1, correct? So 128 plus 8 is 136. Yeah. So this will be, here I will have a 1, this will be 0, then I will have a 1, then again I will have a 1, then I will have zeros. Okay, I will have zeros till what? So this is 2 raised to power 7, correct? So the 8-bit position will be high. So 1 0 1 2 0 1 2 3 4 5 6 7. So yeah, this will be high. So overall I have 8 bits here. Okay, so now my tag, anyways, like this is wrong, we don't need to anyways check it because first one is wrong, right? So I don't need to check the second one, but let's check it for the sake of it. So this will be 10, tag is 10, so tag is 10. My cache block number is 00. This is the cache block number and this is the byte offset. So if I go into cache block number 00, I see 10 is there, tag 10 is there, but okay, this is present, but this is not present, right? So automatically this option is gone. Okay, automatically this option is gone. Let's check the second option. So in the second option, they have given that 152 and 128 are in the cache. 152. So 152, if I want to write in terms of binary, so this will be 128 plus 22 plus 22. So 22 will be 16 plus 6. So it will be 16 plus 6, 16 plus 4 plus 2. So this will be 128 plus 16, 128 plus 16. So this will be 134, 134 plus 10, 144, 144 plus 4, 145, okay, something I have done wrong. Okay, 148 plus, okay, sorry, hold on. 128 plus 6, how much I need? 128, I need another 4, 34, I need 34. Sorry, I need 24. Sorry, this will be 4, right? I need 24. If I need 24, then this will be 16 plus 8. That should be enough. Yeah. So this will be equals to, again, this bit position will be high. I will have zeros, and this bit position will be high, and the before bit position also will be high. So 1 0 0 1 1 0 0 0, I guess. So this is the 0 1 2 3. So 2 raised to power 3 is 8. 2 raised to power 4 is 16. 4 5 6 7. Yeah, it is correct. So this is the binary. So from here, if I see the tag is 10, the cache block number is 01, and the byte offset is 100. So here the cache number is 01 and the block number is 10. Okay, so sorry, tag number is 10. So if I go to 01 cache, is it 10? Yes, it is 10. So it is a match. So if it's a match, so 152 actually exists in the cache memory. Let's check for the other one, that is, which one is the other one? Other one is 128. So 128 is actually very simple. 128 is only 128 only. Okay, so it will be equals to, only this bit will be high, all rest of the bits will be 0. So 0 0 0 0. Okay, so here these 4 bits are there and these 4 bits are there. So out of these 4 bits, these 2 bits are my tag and these 2 bits are my cache block number. So at cache block number 00, tag should be 10. 00, if I go, tag is 10. Yes, it is matching. So this will be my answer. It is a MCQ, so I will not check the other ones. Okay, so you can verify, that is the homework for you. You check the other ones, you will see that something is missing. Okay, so now let's solve this next question. So consider a computer system with 32-bit address. So main memory has 32-bit address. Each block in the cache stores 64 bytes. So what is the number of bits of the block? Basically the byte offset. Byte offset will be, okay, everything is gone. Okay, byte offset, so it will be equals to log base 2 of 64. So this will be equals to 2 raised to power 8, not 2 raised to power 8, sorry, 2 raised to power 6. So I will have 6 bits for the block size. Now what are they asking? It is a direct map cache with 128 blocks. Okay, fine. For each of the following addresses, determine the specific block line in the cache where the data will be stored. So in the cache, right, I have total 128 blocks. So they are asking in the block, in which line exactly will the cache be stored in the block. So they are basically asking me the byte offset. Byte offset. So finding out byte offset is not that difficult. It will be the last 6 bits, right? The last bits are the byte offset. So last 6 bits will be the byte offset. So they are asking last 6 bits of the memory address. So just check the last 6 bits. So if I okay, they are asking me exact line in the cache where the data would be located. Yes, that is what they are asking. So only the last 6 bits are required. So in this case, what is the last 6 bits? In this case, the last 6 bits is, like, if I break it down into, this is in hex, if I break it down into binary, this will be 0001 and then 0010. Yeah, this will be the binary equivalent. So the last 6 bits, this is the 3 and 3. So this is the total byte offset in this case. So byte offset will be what? This will be basically yeah, this will be 0010010. Okay, here again the same thing, right? Just check the last 8 bits and just trim out the last 6 bits. So if I trim out the last 6 bits, it will be all ones. Okay, all ones. Same here as well. Okay, you can follow the same thing. So this is the homework for you. This I hope you can do. Okay, I'm not doing it for you, I'm just giving you example that just trim out the last 6 bits and that will give you the byte line number. Okay, this was very easy question. Let's do this last question of today's lecture. So in this question we have to consider a cache with 2 raised to power 13 blocks. Okay, so if it has 2 raised to power 13 blocks, so is it a direct memory? Is it direct map? No, it is not direct map. Okay, so number of blocks of blocks equals to 2 raised to power 13. Okay, number of blocks are equals to 2 raised to power 13 and each block size is 32 bytes. So basically number of bits in byte offset. This will be log of 232. So this will be 5 bits. Okay, the cache controller stores one valid bit, one modified bit and tag bits for each metadata. So extra tag bits are what? Extra tag bits equals to 2 because one valid bit and one modified bit and tag bit, that remaining tag bit is already there. The cache controller has maximum memory capacity of 8 kilobytes to store the metadata. So basically they have given me indirectly the tag directory size. Tag directory size is 18 kilobytes. 18 kilobytes. So it will be 8 into 2 raised to power 10 bytes. Okay, so the cache is organized as a k-way set associative cache. What is the maximum value of k that can utilize the cache controller fully? So I want to utilize the cache controller fully. Basically I want to, whatever the memory I have in the cache controller, that is 18 kilobytes, I want to utilize it fully. So if I break down my main memory address. Main memory address is of how many bits? Main memory address is of total 32 bits. So this whole thing is 32 bits. 32 bits, and out of which the byte offset is of 5, right? Byte offset is of 5 bits. So this is 5 bits. That is the byte offset. And here I will have the set offset for set associative mapping, and this will be the tag. Now, if let's say it is k way set, if it is k way set, what are the number of sets? So the number of sets the number of sets equals to 2 raised to power k. Number of set equals to 2 raised to power k. Okay, so what I can do, okay, so not number of sets, sorry, what I'm telling, not number of sets, sorry, number of sets is k, it is k way set, that means I have 4 total k sets, right? So now I need to find out the number of sets in the cache. Okay, this will be equals to what? This will be total number of blocks divided by the number of sets. Okay, total number of blocks is 2 raised to power 13 divided by the number of sets. That will give me the number of sets in the cache. Now actually, how much do I want this to be? How much do I want this to be? So I need to maximize my tag directory, right? So what is this tag directory size equals to? This tag directory size is equal to the tag bits plus the extra bits, that is 2, into the number of blocks of the cache memory, that is 2 raised to power 13. Okay, this is the tag directory size in bytes, correct? Number of blocks 2 raised to power 13 in bytes. So this is in bits, actually this is in bits. So if I want to convert this in bytes, this will be tag plus 2 into 2 raised to power 10 bytes, because if I divide by 8, this will be converted into bytes. Okay, so now this is equals to 18 into 2 raised to power 10. So 2 raised to power 10, 2 raised to power 10 cancels each other out, because automatically byte is cancelling out. So my number of tag bit, so I need the tag bit to be 16. So tag bit, the tag should have 16 bits. Okay, to maximally utilize my tag directory. So if it is 16, if it is 5, so this will be what? This will be 11. So my set offset will be 11 bits. So if set offset is 11 bits, so number of sets will be equals to what? Number of sets will be 2 raised to power 11, because if I have 11 bits in the set, so total number of sets will be 2 raised to power 11. So from here I can directly get my value of k. The value of k will be 2 raised to power 2, that is 4. Okay, that is the answer of this question. This question is very elegant. Okay, very good, very elegant question. So if you are having doubt, please read, go through the set associative mapping, and then just come back here. If you are having doubt, that means you have not revised well. Okay, so go back and read that and now come back here. Okay, so then you will understand this question. So that's it basically for this lecture. I hope you have enjoyed this lecture. If you did, make sure to hit the like button, make sure to comment down below which particular concept you enjoyed the most, and I will see you in the next lecture. Until then, happy learning.